So with all that cool technology, what have we actually learned? Well, by careful study of these seismic waves, okay, as recorded by the seismographs, seismometers, okay, different in different locations. There's one guy in Croatia he's got a big long name, Mohorovic, okay, Mohorovic, or something like that. Anyway, as you discovered in the reading, they've shortened that up to Moho. All right, and he's using the seismographs and stuff. He came to the conclusion that the Earth, that mantle layer, wasn't the same throughout its the entire layer. He figured out that, or he made the postulated the idea that many miles below the surface there's this border. Okay, kind of like in the atmosphere we have the tropopause and the stratopause and all those. Well, there's kind of this layer in between, and it was named after him, called the Moho. Right, this border it's actually called the Moho discontinuity. Okay, now we know that marks the boundary between the Earth's crust and the beginning of the Earth's mantle, and we also know in the mantle that it's actually more dense than that of the crust. And as one travels deeper into the core, matter becomes even more tightly packed. And at the same time, the temperature of the rock in the mantle goes up the deeper you go. To give you an idea of the temperatures, at the Moho, the temperature's around 1,000 degrees Fahrenheit or 500 degrees C. While you get to the lower portion of the mantle, it gets as hot as 7,000 degrees Fahrenheit or 4,000 degrees centigrade Celsius. Now, that's some pretty hot rock. Okay? And as you might expect, the pressure that the rock is under increases with the increasing depth as well. And after all, think about it. Remember when we talked about the atmosphere? The more stuff you have above it, the more pressure there is on it. Same thing's happening in the Earth. The more rock there is above it, the more weight that's pressing down on it. So by the time you reach the bottom of the mantle, the pressure is about 1.4 million times that of atmospheric pressure. And that pressure and temperature increase as you travel deeper into the mantle leads to some very interesting effects. What it does is in the upper part of the mantle, it's composed of solid rock. Okay, this and the crust above it are called the lithosphere, right? We've seen that before. But below the lithosphere, there's this small portion of the mantle called the asthenosphere. At the pressure and temperature found in the asthenosphere, rock is not completely solid. It behaves more like, thick syrup flowing around in the mantle. And what's interesting is when it's subjected to an abrupt force, like punching it or something, that syrup hardens into a firm solid. And then after the force goes away, the rock goes back to being syrupy, thick, gooey stuff. Scientists call this plastic rock. Now, I didn't have you do the experiment, but we can actually recreate that, and get the same effect. And if you want to, you can go explore that. Maybe, I know some of you have grandchildren. Maybe you want to go do that with your grandkids or kids. It's fun to play with. So if you want to, you can go check that out. But it's I just bring that to your attention if you want to play with it. But let's talk about plastic rock. Like I said, it behaves. When you leave it alone, it kind of flows. But if you push on it or punch it or apply a force to it, it just gets solid almost instantaneously. And just a reminder that happens in the asthenosphere, where we have that combination of temperature and pressure that makes that rock that's in that layer be that plastic rock. Alrighty, couple questions to check your understanding, and then do those, and then come on back and we'll keep going with today's lecture.